Before we dive into any specific pattern, we need to answer a more fundamental question. What exactly is a design pattern, and why do developers bother learning a whole catalog of them? That is what this lesson is about. We will build a clear mental model from the ground up, so every pattern you learn afterward has a solid foundation to rest on. Here is the pain that patterns exist to solve. As your codebase grows, objects need to communicate, share state, or be created in flexible ways. The instinct is to wire them together directly and move on. But that tight coupling means a small requirement change ripples through the entire system. Worse, every team member independently invents their own solution, and no one has a shared name for what they built. Think about how a building architect works. When a project needs a staircase, they do not sit down and invent a new structural form. They pick from a set of well-understood designs, each one named, each one carrying known strengths and known costs. A design pattern in software works exactly the same way. It is a proven named blueprint for a recurring structural problem, not a piece of code you paste in, but a plan you adapt to your situation. The term pattern was borrowed from architect Christopher Alexander, who catalogued recurring solutions to problems in towns and buildings. In 1994, four authors known as the Gang of Four applied the same idea to object-oriented software in a book simply called Design Patterns. A pattern, as they defined it, always has four parts: the context in which the problem arises, the problem itself, the solution structure, and the consequences, both the benefits and the trade-offs. Let us look at a tiny but complete example to make this concrete: the singleton pattern. First, the constructor is marked private, so no code outside the class can call new config directly. Next, a static field called instance holds the one and only object, starting as null. The static method getInstance checks whether instance is null. If it is, it creates the object and stores it. If it is not, it returns the existing one. Down in the client code, both A and B call getInstance, and the strict equality check confirms they hold the exact same object. The point here is not just the mechanics. It is that the moment you say this is a singleton, every developer on your team instantly understands the intent, the structure, and the trade-offs without reading a single line of code. What makes a pattern more powerful than a code snippet is that it bundles four things together. The context tells you when the problem typically shows up. The problem names the forces in tension. Maybe you need flexibility but also simplicity. The solution describes the arrangement of roles and relationships, not a rigid class hierarchy. And the consequences are honest about what you gain and what you pay. Patterns always add some indirection, and that is a real cost worth knowing upfront. Patterns are tools, not rules, and using the wrong tool is just as harmful as using no tool at all. Reach for a pattern when a structural problem genuinely recurs, when your team needs a shared name for a design decision, or when you know a specific dimension of the design will need to change. Skip a pattern when a simple function solves it cleanly, when the extra indirection buys nothing, or when your honest reason for using it is practice rather than necessity. That last one is fine in a side project, just do not do it in production code. Let us lock in the four things to carry forward. A pattern is a named reusable solution to a recurring design problem, not a snippet you paste in. It always bundles context, problem, solution, and consequences. Its greatest value is as vocabulary. Saying observer or factory communicates an entire design decision instantly to anyone who knows the term. And finally, the discipline that separates good pattern use from over-engineering is always asking, is this problem real, is it recurring, and does the pattern's cost actually pay off here?